successfully conveying value and interpreting great books from around the world. Hello, this is Sally's Book Talk. Today I'm interpreting the book, The Information, A History, a Theory, a Flood. The author of this book is James Gleick, a reporter and editor for the New York Times, and he's also a renowned popular science writer. Popular science books sell in the millions. The English title of The Information directly translates to information, its history, its theory, and the flood it unleashed. Based on the title, today's interpretation is divided into three parts. First, we'll cover the history of information, then introduce the information theory founded by Shannon, and finally discuss the impact of information. Let's start with the history of information. Information has a key trait. It can only be perceived by the masses through dissemination. Therefore, Gleick's take on information history is essentially the history of how information dissemination tools evolved. We begin with the talking drums of Africa. Europeans arrived in sub-Saharan Africa quite late. Back then, these African tribes lived primitive lives, hunting for survival, without writing, but each tribe always had a drum, carved from a single log, about over a meter long. Early on, these drums conveyed simple messages, like enemy attacks, requests for support from neighboring villages, or notifications. When tribes gathered for battle, they relayed commands such as advance or retreat. Over time, the meanings conveyed by drum sounds gradually became more complex. A missionary named Roger Clark recorded a drum call summoning villagers to a funeral and translated its meaning. At dawn, let's not assemble for work. We'll gather by the river for a meeting. He also noticed that while only some knew how to communicate with drums, almost everyone understood their meanings. Even if drummers varied in rhythm, it didn't stop them from conveying the same message. In just an hour, info could travel 100 to 200 kilometers. The second tool for spreading information is writing. The ancient Greek culture we know today largely stems from Homer's epics, which Homer compiled from oral traditions. So why not use language itself as a tool for spreading information? The book explains that language isn't a technology. No matter how mature or advanced, it can't be seen as external to the mind. Because language is a function of the mind itself, while writing is an external symbol. It seems to extract knowledge from people and store memories elsewhere. This conveys a characteristic of information dissemination tools. They are independent of the mind. In other words, the dissemination tools themselves carry no emotional stance or cognition. Writing allows information to break through the limitations of time and space. However, this also brings new problems. Plato worriedly said that writing would lead to rigidity, which can be understood from two aspects. Firstly, writing causes the emotion carried by spoken words to disappear. Secondly, the copying of text can produce errors, leading to incorrect dissemination of information. To prevent the latter scenario, logic and dictionaries emerged. The original purpose of logic was to make thinking rigorous and ensure correctness, which also lends rigor to written expressions of ideas, safeguarding accurate information dissemination. For example, Aristotle proposed the logical syllogism. If you find a passage by Aristotle that doesn't conform to syllogism, it must be a printing error, thus safeguarding the text. And then there's dictionaries. The book mentions the English dictionary compiled by village teacher Robert Cowdrey in 1604, arranged alphabetically. Cowdrey titled his book, The Table Alphabetical. This was to emphasize that his dictionary was arranged in alphabetical order. At that time, the popular arrangement was by word meaning, like heaven, earth, humans, animals, plants, etc. Cowdrey's method later became known as the dictionary arrangement, providing lookup convenience for readers unfamiliar with word meanings. From drums and writing, can you perceive some characteristics of information transmission? They can convey identical information but manifest quite differently. That is, information must be modulated during transmission and restored at reception, what we now call encoding and decoding. Secondly, errors are inevitable during transmission. requiring effective methods for detection and correction. African drums used redundancy to eliminate errors. For instance, notifying villagers of a morning gathering, according to missionary Clark's records, used as many notes as, "At dawn, let's not assemble for work. We'll gather by the river for a meeting."
Writing, meanwhile, uses logic and dictionaries to standardize expression. The third carrier is machine computation, distinct from modern computers.
Here we mention two 19th century English figures, Charles Babbage and Ada Byron.
The former was a mathematician and inventor who held the Lucasian Chair of Mathematics at Trinity College, Cambridge, a position once held by Newton. The latter was the wife of the Earl of Lovelace, daughter of the poet Byron, and a passionate mathematician.
Babbage was appointed to the Lucasian Chair not for groundbreaking mathematical achievements, but for rescuing British mathematics. In 1810, the 19-year-old Babbage entered Trinity College, Cambridge, but he quickly became disappointed, realizing he knew more than his professors. So Babbage crossed the English Channel to study in France, learning Europe's most advanced mathematics and resolving to revive British mathematics. He eventually succeeded by co-founding the Analytical Society, introducing Leibniz's theories, and reforming British mathematics. In the 18th century, logarithmic tables flourished in Europe because logarithms drastically reduced computational complexity. Babbage conceived a machine to produce these tables, naming it the difference engine. Supported by the British Treasury, Babbage spent 10 years building a working prototype still displayed in London's Science Museum. But at that point, disputes arose with his partner, and the Treasury lost patience with Babbage's project. Thus, the full difference engine was never completed. Babbage regularly hosted salons at his home. Attendees included British dignitaries, artists, and scientists like Darwin, Faraday, and Dickens, all frequent guests. It was at such gatherings that Ada Byron met Babbage. Other guests' reactions upon seeing this intricate machine, I dare say, resembled a savage's first encounter with a large mirror or gunshot. Yet Miss Byron, despite her youth, grasped its mechanics and recognized its brilliance. An attendee described Ada's reaction to the analytical engine. Her exchanges with Babbage made him feel he'd met a true intellectual companion. Babbage told Ada he'd lost interest in the difference engine and was designing a new computational machine called the analytical engine. As the name suggests, this machine could think. Thereafter, Ada became not only Babbage's intellectual partner, but also the source of much of his inspiration. Even after Ada got married and had children, she still frequently corresponded with Babbage to discuss machine computing issues. Ada said that the analytical engine shares no common foundation with mere computing machines. It signifies the development of a new, comprehensive, and powerful language. She attempted to use this idea to create a program for calculating Bernoulli numbers, employing what we now call loop statements. The original text of Ada's program was only made public in 1953, when people first read it, honoring her as the first programmer in human history. In 1980, the U.S. Department of Defense proposed a new computer language, named the Ada language. Although Babbage's difference engine and analytical engine were never fully built, his concepts, especially the analytical engine, became the prototype for future computers. For this reason, we call it the zeroth generation computer. The contribution of zeroth generation computing was linking the storage and generation of information to computing machines. The fourth carrier for disseminating information is the telegraph. In the 18th century, people understood electricity and knew it could be transmitted over long distances. From then on, people wanted to use electricity to transmit information. Now, scientists knew that electricity flows from positive to negative poles and created ammeters to detect current direction. The great mathematician Gauss was among the first experimenters to use ammeters for transmitting information with electricity. He connected the transmitting and receiving ends with 3 wires. Hell, Oh, these three wires were connected to the positive, negative, and ground poles of the power source, using a key to select whether to send positive or negative electricity. At the receiving end, an observer watched the ammeter and recorded the deflections of the pointer. Gauss and his team defined the correspondence between pointer deflections and letters. One right movement for A, two for I, one left for E, two for B, two movements right then left for O, two movements left then right for U, two movements for B, two movements right then left for O, two movements left then right for U, and so on. This method indeed linked ammeter pointer deflections to letters, enabling remote transmission of words, but it was very inconvenient, transmitting only about 3 letters per minute.
Later telegraphs adopted Morse code, invented by Americans Morse and Vail, which uses dots and dashes based on the duration of key presses, equivalent to today's zeros and ones. And Vail invented the key for transmitting and automatic recording devices at the receiving end, allowing automatic recording of telegraph messages. And
Morse assigned codes to the 26 English letters and 10 digits based on transmission frequency, creating Morse code. An average operator could send at least 30 letters or numbers per minute. Have you noticed that Morse code's dots and dashes are equivalent to today's binary digits of 0 and 1? These dots and dashes completely replaced written words in signal transmission, and the telegraph led to the birth of cryptography. For example, A sends B a telegram. They'd pre-agreed on the number 3. The correct Morse for ask is 001111111111111111, but the sender added 1 before transmission, resulting in 00011101110 0110 decoded normally as DVN, only the recipient knew beforehand. About the number 3. Shifting backward 3 letters in the code table retrieved the correct message. This process is called encryption. The number 3 is called the encryption key. Encryption's emergence marked a major milestone in information transmission. It shows information modulation and restoration during transmission can be customized. All right, we've covered the 4 generations of info tools: drums, writing, machines, and telegraph. Now on to information theory. We'll introduce 3 masters and their contributions. First is American Claude Elwood Shannon, 1916 to 201, widely regarded as the founder of information theory. In 1948, Shannon published A Mathematical Theory of Communication, the first book dedicated to communication studies. It described information transmission processes and crucially defined how to measure information. In 1936, Shannon graduated from the University of Michigan, then went to MIT for graduate studies. His specific role was operating the differential analyzer for engineering Dean Vannevar Bush. This 100-ton behemoth was fundamentally mechanical, designed to solve differential equations. After inputting parameters, it could plot solution curves for differential equations. A key component was the relay, an electrically controlled switch. In 1937, Shannon interned at Bell Labs, deeply studying relays. He linked their 2 states, open or closed, to digits 1 or 0, then applied Boolean algebra to analyze interconnected relay outcomes. Boolean algebra emerged in the mid-19th century but remained largely overlooked for decades. This research formed the core of Shannon's master's thesis. Given Shannon's findings, his advisor suggested he pursue a PhD in mathematics. Though enrolled in mathematics, Shannon maintained his academic relationship with Bush. In a letter to Bush, he outlined his research on information transmission. He stated that nearly all communication systems involve 2 functions and 2 transformations. The sender's intended message to the receiver is function F, but during transmission, this function gets transformed into another function F. Thus, the receiver gets F, then uses specific equipment, essentially a key, to convert F back to F, achieving precise replication. Shannon noted that perfect replication is nearly impossible. Some distortion always occurs. Estimating and eliminating noise thus becomes communication's critical task. Shannon observed that encryption essentially adds artificial noise, preventing ordinary replication. Due to his cryptographic insights, during 113, Shannon was stationed at Bell Labs' old New York building. His specific mission: analyze security of encrypted communications between President Roosevelt and Prime Minister Churchill. Theoretically, all ciphers are crackable, but only with sufficient historical data to deduce the key. He discovered cracking the leader's cipher required at least 50 samples, but their random cipher changed keys before adversaries could gather enough, making it uncrackable with current tech. In 1945, Shannon compiled this into his paper, A Mathematical Theory of Cryptography. This paper remained classified by the U.S. government for decades. We credit Shannon with founding information theory, chiefly because he introduced entropy into it. How are these two connected? First, information in this theory relates to but differs from everyday usage. Don't confuse them. Shannon said information relates to uncertainty. It emerges from uncertainty. Shannon conceived using entropy to quantify information. Entropy, originally from thermodynamics, measures thermal energy's work potential. So how does entropy describe information? If an event H has n possible outcomes with known probabilities P1, P2, P3, etc., we can calculate its entropy using a formula.
If the event has only one outcome, then n equals 1, P1 equals 1, and entropy H equals 0.
If the event has two equally probable outcomes, n equals 2, P1 equals P2 equals 0.5, the calculated entropy equals 1.
Further, with two outcomes of unequal probability, say 1/4 and 3/4, the entropy calculates to approximately 0.811.
Shannon expressed these results using bits as the unit. Thus, when n equals 1, a certain event, entropy is 0 bits. With two equally likely outcomes, entropy is 1 bit. With two unequal outcomes, here entropy drops below 1 bit. Higher entropy means greater uncertainty, while information reduces uncertainty by decreasing entropy. Shannon's introduction of entropy into information theory, complete with calculation formulas and units, signaled the field's establishment.
In the 1950s, information theory became wildly popular, with many fields attempting to mimic its approach.
However, Shannon cautioned that information theory is fundamentally mathematical. While useful across disciplines, it shouldn't be crudely transplanted. Our second figure is the renowned Alan Turing, hailed as the father of computer science, a British pioneer. Born in 1912 and died in 1954, Turing earned his PhD from Princeton's Institute for Advanced Study in 1938. He later returned to Cambridge University. During World War II, British intelligence recruited him to decrypt German communications, the Enigma cipher machine. Messages typed normally would be automatically converted to cycraft via machine settings. Even operators didn't know the output. Only recipients using Enigma machines could decipher the intelligence correctly. Turing cracked Enigma at Britain's Bletchley Park, building a 3 cubic meter machine specifically for decryption. In 1943, Turing traveled to America aboard the Queen Elizabeth liner, only possible because his code-breaking helped evade German submarine attacks. But in the U.S., Turing and Shannon often lunched together at Bell Labs' cafeteria. Though both worked with codes, one creating them, one breaking them, national secrecy meant they never discussed cryptography.
Their shared passion was computing, then called electronic brains.
Over meals, they frequently debated encoding problems. Turing shared his machine programs, Shannon explored relay encodings. Both mapped concrete phenomena to mathematics. At Bell Labs, Shannon ultimately developed algebraic methods for cryptography. Meanwhile, at Cambridge, Turing conceptualized the Turing machine, a computer theory. Though never built, it's now ubiquitous. Turing envisioned this machine with components like symbols and states, defining their construction and operations meticulously. He named it U for universal, meaning all-purpose.
He proved it could solve polynomial equations, calculate pi, and derive natural logarithm bases.
It also demonstrated uncomputable numbers exist. In fact, most numbers are uncomputable. Modern computer design still operates within the Turing machine framework. The third key figure is American Norbert Wiener, 1994 to 1964, known as a prodigy since 1915. He graduated from Tufts math program at 14, earning a Harvard PhD at 18. After Harvard, he studied in Europe under math giants Russell, Hardy, Landau, and Hilbert. In 1919, Wiener returned to teach at MIT. During War II, he was among first recruited for U.S. artillery control. His noise processing work became Wiener filtering. With colleague Bigelow, he turned artillery's aircraft tracking behavior servo control. Wiener's most famous work is his slim volume, Cybernetics, or Control and Communication in the Animal and the Machine. In 1948, this highly technical academic work, Cybernetics, was simultaneously published in the US and France, and surprisingly, became a bestseller that year. Its core concept is negative feedback. Wiener believed negative feedback is fundamental to control behaviors in both animals and machines. He noted that closed-loop control systems operate not on targets, but on deviations between current status and goals. His artillery control designs followed this principle. Wiener emphasized, this deviation is information itself, information that reduces aimlessness. Finally, let's discuss information's tidal waves. First wave, cracking the genetic code. Early on, people noticed children resemble parents. For example, an overweight father has an overweight daughter. People say he passed on obesity. But how? By late 19th century, chemists knew molecules or ions. Physicists knew electrons or atoms or neutrons. Thus, biologists assumed life must consist of some particle. They proposed genes as life's fundamental particles. Daughter inherits father's fat gene. Yet, biologists couldn't physically locate genes. In 1910, Danish botanist Johansen coined gene, explaining it might not be physical matter, meaning genes could be information. Mendel first proved genes' existence using yellow or green peas. Hybrid offspring were either yellow or green, no intermediates. He called them hereditary factors. And he stated these factors don't blend or diffuse, remaining unchanged through heredity. Though Mendel didn't use gene, he confirmed something crucial governs inheritance. Popularizing influence goes to Schrödinger, the quantum mechanics pioneer, who accepted the concept. But he puzzled. How could such tiny matter control an organism's entire developmental script? Innovative analogy concluding the Morse code through combinations, thus introducing encoding to genetics. In the late 19th century, chromosomes were discovered. During cell division, they split and replicate. And thus, it's reasonable to conclude that genes carrying hereditary traits reside within chromosomes. In the 1950s, Austrian biologist Chargaff and colleagues proposed that a chromosome is a linearly encoded instruction. The entire chromosome is a message. It determines an organism's developmental stages. Note, linear means ordered sequence without crossover. In 1953, biologists James Watson and Francis Crick published in Nature claiming they'd found genes. It was known chromosomes contained 4 components, with proteins and DNA being major ones. After ruling out proteins as gene carriers, Watson and Crick believed genes must hide in DNA. Chemists had discovered DNA comprises nucleotides, each with one of 4 bases. A, C, G, T. Watson and Crick discovered DNA's double helix, 2 intertwined strands connected by base pairs. Their one-page Nature paper announced this and predicted, we imagine base pairing directly suggests a replication mechanism for genetic material. In a follow-up paper, they proposed precise base sequences carry genetic coding, earning them the Nobel Prize. Now we can answer why both father and daughter are overweight. It's widely accepted that heredity works through genes, encoded base sequences within chromosomes. The daughter inherits obesity because the father passed the fat gene via the fertilized egg. In this sense, heredity is purely an information transfer process. The complete blueprint of an organism is written in the fertilized egg. The second and third waves impacted cultural development and randomness theory. Information science's cultural impact mirrors how genetic theory replicates in sociocultural inheritance. In 1970, British biologist Richard Dawkins published a book titled The Selfish Gene. Mimicking gene, he coined meme, rated as momen in Chinese, forming meme theory or cultural evolution. He believes cultural development is inherited too, just like biological genetics, with memes replacing genes residing in human brains to pass on. If height, weight, and eye size are genetic expressions, then pop culture trends and social behaviors are manifestations of memes. If genes carry biological information and heredity transmits it, then memes carry cultural information. The root of societal evolution lies in cultural information transmission. The foundation of randomness theory was laid by Soviet mathematicians. Kolmogorov enriched Shannon's research. Academia terms his contributions algorithmic information theory. Kolmogorov proposed 3 information sources: combinatorial, probabilistic, and algorithmic. Shannon covered combinatorial and probabilistic, but algorithmic information was first introduced by Kolmogorov. Computing a number requires programs, some simple, some complex. Thus, in algorithmic info theory, Kolmogorov defined complexity proportional to program intricacy and the number's information content. Some numbers need short algorithms. Others don't. These non-compressible numbers are called random numbers. And then, random numbers have greater uncertainty, meaning higher entropy. Wave after wave passed, bringing us to the internet-dominated era. What's the world like after these tides?
One phenomenon is information overload. Countless digital repositories created, with data persistence and unforgetfulness causing massive management chaos.
Wikipedia exemplifies this. Anyone can write or edit articles. Search Babler on Wikipedia. You'll find multiple conflicting interpretations, often impossible to verify. You can't identify which explanation you need, nor confirm if your chosen one is correct. Wikipedia maintainers argue it's not a crisis. Their time isn't ours to control. We can't complain about useless work. They're not obstructing anything. Let them write. This is the information explosion, increasing entropy, eroding authority, and amplifying chaos. The second phenomenon after the flood is the explosive growth of storage technology. Shannon once estimated the Library of Congress held about 10 terabytes of information. Today, the library also collects digital materials. By February 2010, it reached 160 terabytes. That's 16 times Shannon's era, showcasing modern storage capabilities. Without physical expansion, data grew 16-fold. Now cloud technology exists. People don't know where the cloud resides, yet store information there, capacity beyond estimation. With daily information creation, could the universe rupture from overload? MIT engineer Seth Lloyd conducted research on this. He said the universe is a giant quantum computer. Its existence records and processes information through evolution. The author closes with this quote for reassurance. Relax, dear humans. Everything's under control. That concludes the information. Leading notes are below the audio. Until next time,